Hey, Matt Mathersum here with Math Madness. Thank you so much for joining us and being a part of the program today. We appreciate it. Over the past couple of weeks, we have been dealing with derivatives. Now, if you don't know what derivatives are, simply put, it's just a rate of change. Well, today we're going to be stepping it up a notch with those derivatives, and we will be getting into differential calculus, okay? Don't get scared. This example today is going to be very, very basic, very simple, and we're going to have a very good understanding by the time this episode is over. Now, if you're already working in this field with differential calculations like this, maybe you have been dealing with something along the lines of beta decay, and you might have seen a differential equation, something along the lines of dx over dt is equal to minus some proportionality constant with a population x, and you would be trying to create a formula, an equation to solve for this particular population at time t, right? So we will be getting to problems like this. Now, you may be thinking, well, why are we interested in something along the lines of, I don't know, looking at beta decay of an isotope carbon-14? Well, during beta decay, you can analyze what happens to a neutron when it changes from a photon to an electron to an antineutrino. That's part of why you look and see what's going on with beta decay, trying to solve for this particular population with respect to time. And when we do get into this, I'll even show you why this side is equal to this. It'll look along the lines of something like this. Raise the k to the t, okay? We won't be getting into this today, though. I just wanted to demonstrate what kind of problems we will be getting into should you decide to stick around and join me for this journey into the abyss, okay? And if this does scare you and you have decided to tune out, I don't blame you. I might too. All right, but enough of that, talking about what we're not going to be talking about after I've already talked about it. Let me erase this and talk about what we're going to get into today, which is, we already said, differential calculus. Well, over here to my right, you can see that I've already got us a graph set up. And it looks like I've got some sort of time going on here on the x-axis. I've got a pricing situation going on the y-axis. And then I have a slope of a line that indicates what's going on with p respect to time, don't I? Well, I do. Well, we know how to calculate the slope of a line, don't we? Sure we do. What is it? Well, we know it's just delta y over delta x, don't we? Well, since we're dealing with price and time, can we just change the delta y and delta x, and let's make it delta p over delta t, okay? And do we understand what I mean when I say delta? We're talking about the change. And when we talk about change, what are we talking about? Yeah, we're talking about the small change in price with respect to time. How much does this change with respect to this? That's just simple subtraction, isn't it? Okay, fine. Well, what is the delta P over delta T? Well, it's 10 cents, isn't it? Because I can see here it's 240, it's 250, it's 260. So delta P to delta T is 10 cents, but it's not just 10 cents, it's 10 cents per month because this is month. All right, well, that's wonderful. Now let's talk about what this price is pertaining to. We need context, don't we? So let's just say that we want to know what the price of peanut butter. Let's say this is the price of peanut butter. We can see that it's going up and up and up every month. And it's not just peanut butter, my friends. It's crunchy peanut butter. The only kind that Matt Mathersum would ever put into his body. Attention peanut butter advertisers, you too can reach this prime demographic, or the second derivative of this prime demographic. Well, anyway, that's all the peanut butter derivative jokes I have. Let's go ahead and get to this mess right here, right now. Okay. Well, we can see that it's going up by 10 cents each month with respect to time. Okay. Well, since we know that the slope of a line is a constant, it indicates the rate of change. I can rewrite this. As, you know what? Let me just rewrite it up here and get rid of this and make this cleaner. I'm doing a lot of erasing today, but nevertheless, it'll look good when we're done. Maybe. You've seen my handwriting before, so it may not. All right, so we can say dp over dt equals delta p over delta t, and that is 10 cents per month. Okay. All right. Well, what were we trying to solve for? Well, we want to know what the peanut butter cost is going to be a year from now. I may have not stated that initially, a lot going on here, but we want to know what the price of peanut butter is going to be a year from now. Well, how do we calculate that? How do I get that kind of information with this? Well, I have to have an initial condition, don't I? Right? So let's get to that. How do I solve for that? Okay, let's go ahead and we're trying to solve for the price. So what do? Well, we know that we can just isolate for P, and that's going to be equal to, we know it's 10 cents per month. So let's give us, you know what, I don't even need that. It's going to be 10 cents times time plus C. Now, what does the C stand for? What is the C? Well, that's the constant that's going to be the initial condition, okay? We need to know what this initial condition is in order to solve this differential equation. How do we solve for C? I want you to look at that for just a second. It might look a little tricky, but it's really not. Just think basic algebra. What do we do when we're trying to solve for something? We're talking about isolation operations, aren't we? Okay, fine. So let's go ahead and plug in the numbers that we have and order to solve for C. Well, I know I've got $2.40 and FYI information. This is all going to be in cents. So this is going to be 240 cents, 250, and so forth and so on. So I know for the month one, I've got $2.40 or 240 cents. So let's go ahead and plug that number in. And that's just going to be 240. Now, I'm going to isolate for the C, right? So I know time is 1. So 10 times 1 gives me 10. So let me bring the 10 over here. I'm going to subtract 10 from the 240, giving us 230, okay? Maybe I went a little fast here. Let's take a minute to look at this, okay? I'm trying to solve for C. I'm trying to solve for our initial condition. Our time at month 1, right? I plug that in. 10 times 1 gives me 10. I'm bringing the 10 over. I'm subtracting that from our initial value, 240, and giving me 230. Where does this 230 go? We've solved the differential equation now. That's the linchpin. That's what's holding us up, is this initial condition. Well, the 230 is the initial condition. All right. Well, guess what? Now we have solved, I guess I can reach that C too. We have now solved the differential equation, and we can solve for peanut butter for today, tomorrow, 500 million years from now with this one simple equation. I kid you not. All right, let's go ahead and do that. I said what we were looking for. The price of peanut butter is what we're solving for a year from now. That's 12 months out, isn't it? So 10 times 12 plus 230. I know you got your handy dandy calculators. What is that going to give us? Yep, it's going to give us a $3.50 price tag. Can you read that? My God, I think my handwriting gets worse by each episode. So you know what? Let's just say it like this. $3.50 for crunchy peanut butter of Matt Mathersum's favorite peanut butter maker, whichever that may be. Well, that's all the time we have for here on Matt Mathersum. Thank you so much for joining us. I'll see you really soon.